This module we are going to see in detail direct memory access and IO processor. First, let us see what is meant by direct memory access, which means transfer of data directly between peripheral devices to memory. During DMA transfer, the CPU is idle and has no control of the memory buses. The DMA controller takes control over the buses to manage the transfer directly between the IO devices and memory. In order to transfer the data directly to memory by the DMA controller, the CPU may be placed in an idle state in a variety of ways. One common method used in microprocessor is to disable the buses through special control lines. So, DMA make a request to the memory bus, by enabling bus request line. On seeing the bus request line by the DMA controller, CPU keeps address bus, data bus and read-write control lines in a high impedance state and also enable bus grant line. So on seeing the bus grant line signal, the DMA gets the control, complete the transfer and disable the bus request line. When the DMA disables the bus request line, CPU automatically disables the bus grant line. When DMA takes control of the bus system, it communicates directly with the memory. So here, two types of transfers are possible. One is burst transfer, another one is transferring word by stealing a memory cycle. In a burst transfer, a block of words will be together transferred. This method of transfer is needed for fast access devices such as magnetic disk. This diagram depicts CPU bus signals for DMA transfer. There are two lines. One is coming from the DMA controller to CPU, that is bus request line, and one line when it is granted by the CPU, it is going to the DMA controller, and CPU has other lines for reading data, writing data into the memory and from the memory, and it has address bus and data bus to specify address of the data and to carry data in and to and from the CPU. Initially, DMA initiates the data transfer by enabling bus request line. On seeing the bus request line from the DMA controller, CPU keeps all the data bus, address bus, read and write control lines in a high impedance state. Then it enables bus grant line. When the data transfer is completed, DMA controller disables the bus request line. Immediately, the bus grant line is disabled by CPU and it keeps all its data bus, address bus and read and write lines in a normal state. This diagram depicts the DMA controller. CPU can communicate with the DMA controller by enabling chip select line, that is DMA select and register select. DMA controller can communicate with the CPU by enabling the control lines through data bus. So initially DMA controller makes a bus request. When the bus request is enabled, CPU cannot access the DMA controller. When the bus request is disabled, it can read from or write into all the register supported by the DMA controller. And here are the four register: address bus buffers, address register, word count register, control register. So initially CPU initiate the data transfer by loading data, desired data into these register, and it initiate the operation. DMA controller, it enables requests the bus by enabling bus grant line. Immediately it will be granted by the CPU so that it can directly transfer into the memory. So all this word count register which contain number of words to be read or written. Address register contain the starting location of the memory, and this will be passing through the address buffer register, and that will be kept in an address bus. And DMA can communicate with IO devices through DMA request and DMA acknowledgement lines. The CPU initializes the DMA by sending the following information through the data bus. The first one is the starting address of the memory block where the data are available or where the data are to be stored. Second one, the word count, which is the number of words in the memory block. And third one, control to specify the mode of transfer such as read or write. And the fourth one is control to start the DMA transfer. And the position of the DMA controller among other components in a computer system is illustrated here. The CPU, it communicates with the DMA through the address and data buses as with any interface unit. The DMA has its own address bus which activates DS and RS lines. The CPU initializes its own address which activates the DS and RS lines. CPU initializes the DMA through the data bus. Once the DMA receives the start control from the CPU, it can start the transfer between the peripheral and the memory unit. When the peripheral devices sends the DMA request, the DMA controller activates the BR request line, informing the CPU to relinquish the buses. The CPU responds with bus grant line, informing the DMA that its buses are disabled. The DMA then puts the current value of its address register into the address bus, initiates the RD or WR signal, and sends the DMA acknowledgement to the peripheral devices. Note that RD and WR lines in the DMA controllers are bidirectional. The direction of transfer depends on the status of bus grant line. When PG equal to 0, the read and write are input lines allowing the CPU to communicate with the DMA register. When PG equal to 1, the read and write are the output lines from the DMA controller to a random access memory to specify read or write operation for the data from the peripherals. When the peripheral devices receives the DMA acknowledgements, it puts the word in the data bus or receive a word from the data bus. Thus, the DMA controls the read or write operation and supplies address for the memory. The peripheral unit can then communicate with the memory through the data bus for direct transfer between two units while the CPU is momentarily disabled. For each word that is transferred, the DMA increments its address register and decrements its word count register. If the word count does not reach 0, the DMA checks that the request line coming from the peripherals. For high-speed devices, the line will be active as soon as the previous transfer is completed. The second transfer is then initiated and the process continues until entire block is transferred. If the peripheral speed is slower, the DMA request line may come somewhat later. In this case, the DMA disables the bus request line so that CPU can continue to execute another program. While the peripheral requests a transfer, the DMA requests the bus again. If the word count register reaches 0, the DMA stops any further transfer and remove its bus request. It also informs the CPU of the termination of the transfer. When the CPU responds to the interrupt by the DMA controller, it reads the content of the word count register. The 0 value of this register indicates that all the words were transferred successfully. The CPU can read this register at any time to check the number of words already transferred. A DMA controller can have more than one channel. Each channel has a request and acknowledge pair of lines connected with separate peripherals. The channel has its own address register and word count register within the DMA controller. And when there are more channels employed, a higher priority channel will be serviced first before the lower priority channel. There are few applications in DMA transfer. It is used for fast transfer of information between magnetic disk and memory. It is also useful for updating the display in the interactive terminal. The content of the memory can be transferred to the screen periodically by means of DMA transfer. Thank you. Now, let us see about input-output processor. Instead of having each processor, each interface communicate with the CPU, a computer may incorporate one or more external special processors and assign them the task of communicating directly with all the input-output devices. An input-output processor may be classified as a processor with direct memory access capability that communicate with I/O devices. So in this configuration, the computer system can be divided into a memory unit and a number of processors comprised of the CPU and one or more I/O processors. And each I/O processor take care of input-output task and relieving the CPU from the housekeeping chorus involved in I/O transfer. The processor that communicates with remote terminals over telephone, other communication media in a serial fashion is called as a data communication processor. That is, a processor that communicates with remote terminals over telephone and other communication media in a serial fashion is called as a data communication processor. The I/O processor is similar to a CPU except that it is designed to handle the detail of I/O processing. Unlike the DMA controller that must be set up entirely by the CPU, the I/O processor can fetch and execute its own instruction from memory. So, IOP instructions are specifically designed to facilitate I/O transfers. In addition, the IOP can perform other processing tasks such as arithmetic, logic, branching, and code translation. The next slide, which contains the block diagram of a computer with two processors. The memory unit, which occupies the central position, can communicate with each processor by means of direct memory access. The CPU is responsible for processing data needed in the solution of a computational task. So IOP provide a path for transferring of data between various peripheral devices and to the memory unit. The CPU is usually assigned the task of initiating the IO program. From then onwards, IOP take care of all the data transfer. And this is a diagram. Here we have got a memory unit and central processing unit, and the IO processor is connected to the memory bus, and the peripherals through IO processor they can transfer data to the memory unit, but CPU it initiates the data transfer. And the data format of peripheral devices are differ from the memory and CPU data format. So the IOP has the responsibility of structuring the data words from many different sources of peripheral unit. Data are gathered in IOP at the device rate and bit capacity while the CPU is executing its own program. After the input data are assembled into a memory word, they are transferred to the IOP directly into memory by stealing one memory cycle from the CPU. Similarly, an output word transferred from the memory to the IOP is directed from the IOP to the output devices at the device rate and the bit capacity. The communication between the IOP and the devices attached to it is similar to the program control method of transfer. Communication with the memory is similar to the direct memory access. I repeat, the communication between the IOP and the devices attached to it is similar to the program control method of transfer. Communication with the memory is similar to the direct memory access. Instructions that are read from memory by an IO processor are sometimes called commands to distinguish them from the instructions that are read by the CPU. So for the command which is given to the CPU, which we call as an instruction, but the command which is given to the IO processor, we call as a command. The command words constitute the program for a IO processor. So initially CPU informs the IO processor where to find the command in memory in order to make a transfer. And this diagram clearly explains how CPU communicates with IOP. CPU initially, it is the responsibility of the CPU to initiate the data transfer. So it sends instruction to test IOP path. So IOP transfer the status word to memory location. It is not directly talking with the central processing unit. It stores one word in memory that represents status. If status is okay, CPU reads the word from the memory. If status okay, send start IO instruction to IOP. Then IOP, it access memory for IO program. So how the communication it takes place with the help of the shared memory concept. Then it finds the IOP program, conduct IO transfer using DMA, and finally it prepares a status report. Then after the completion of IO transfer, it interrupts the CPU. Then CPU requests the status. It transfers the status in the memory location and CPU checks the status word for a correct transfer. Like that it continues the process. The IO processor in IBM 370 is called as a channel. The channel is attached to one or more IO devices. There are three types of channel here. One is called multiplexer, second one is selector, and the third one is block multiplexer. The multiplexer channel can be connected to a number of slow and medium speed devices, and it is capable of operating with a number of IO devices simultaneously. The selector channel is designed to handle one IO operation at a time, and it is normally used to control high speed devices. The block multiplexer channel combines the feature of both the multiplexer and the selector channels. It provides a connection to a number of high-speed devices, but all IO transfers are conducted with an entire block of data as compared to the multiplexer channel, which can transfer one byte at a time. Its multiplexer can transfer one byte at a time. Here, the transfer is block of data. Here it can access with multiple number of devices, but selector only one device, high speed device. The CPU communicates directly with the channel through dedicated control lines and indirectly through reserved storage areas in memory. Those words formats are given below. The first one is IO instruction format. It contains operation code, channel address and device address. And second one, channel status word format, which contain key for production, address, status and count. Third one, channel command word format, which contains command code, data address, flags and count. There are 8 IO instructions supported by IBM 370 channel. One is start IO, second one start IO fast release, third one test IO, fourth one is clear IO, fifth one halt IO, sixth one halt device, seventh one is test channel, and eighth one is store channel identification. Addressed channel responds to each of the IO instruction and executes it. It also sets one of the 4 condition code in the processor register called PSW. The CPU can check the condition code in the PSW to determine the result of IO operation. The meaning of the 4 condition are different depends on the IO instruction, but in general they specify whether the channel or the device is busy, whether or not it is operational, whether interrupts are pending, if the IO operation has started successfully, and whether a status word was stored in memory by the channel. The channel status word, which are always being stored in location number 64 in IBM 370, has following 4. component. The first one is the key, second one is address, third one is status, and the fourth one is count. The key field is a protection mechanism used to prevent unauthorized access by one user to information that belongs to another user or to the operating system. The second one is address field. In the status bird gives the address of the last command word which is executed by the channel. Third one, the count field gives the residual count. So that is the number of words we are going to transfer from memory to peripheral or peripheral to memory. And the last one is the status field, which contains the status of the channel and the devices or any error condition. Already we have seen there are 8 commands in IBM 370 channel. The difference between start IO and start IO fast release instruction is that the start IO fast release instruction require less CPU time. That is, it immediately releases CPU for other operation. When the channel receives one of these two instructions, it refers to memory location 72 for the address of the first channel command word. A channel command word format, which is a channel program consisting of is given below, and it consists of command code, data address, flags, and count. The data address field specify the first address of a memory buffer, and the count field gives the number of bytes involved in the transfer. So address field, it contains the first address of a memory buffer. Count specify how many bytes are involved in the transfer. And the command field specify an IO operation. The flag bit provides additional information for the channel. The command field corresponding to an operation code that specify one of the 6 basic type of IO operation, which is given in the next slide. This 6 basic types of operations are write, which transfer data from memory to IO device. Second one is read. This transfer data from IO device to memory. Then we have got read backward. This is being used in magnetic tape with tape moving backward. And fourth one, control, used to intimate an operation not involving transfer of data, such as rewinding of tape or positioning a disk access mechanism. And fifth one is sense. It informs the channel to transfer its channel status word to memory location, as we have studied earlier. Sixth one is transfer in control, used instead of a jump instruction. Here the data address field specifies the address of the next command word to be executed by the channel. It is like a go-to statement. Here is a channel program. This channel program contains 3 instructions. All these 3 instructions are supposed to write on the tape. Here the address is the first command is considered. The starting address is given as 2000. So from the memory location 2000, it will be reading 40 bytes, and the first bit of the flag bit is 1, that represents it is a first command, and all these 40 bytes will be written on the tape. And secondly, we have got a write tape command. The starting memory location is given as 6000, and the second flag bit is set as 1. That means it is a continuation of the previous one. Here we are supposed to read 40 bytes from the location 6000, and these two are combined and will be written on the magnetic tape, which forms one record. And third is again a write tape instruction. The starting address is given as 3000, and all the bits in the flag is 0. That means it is the end of the command. Here we are reading 20 byte, and it will be written on the tape after leaving some gap we call as a inter-record gap. Okay. So we are familiar with IBM 370 channel. it always save the status, channel status word in location number 64, channel address word in location number 72. And it is the responsibility of the CPU to start the IO instruction, IO operation. So CPU program, when it encounters start IO instruction, it gives the starting address of the channel program in location number 72. So location number 72 will give the starting address of a channel program. The IO processor, it takes the responsibility of executing the channel program, and finally it saves the status in channel status file. Hope we have understood IO processor clearly and with direct memory access. Thank you. So far we have learned direct memory access, the DMA controller, DMA transfer, and IO processor, and how it communicates with CPU, and an example of an IO processor, that is IBM 370 IO channel. Hope you all have understood clearly. Thank you once again.